Right, we're going to have a look at the floppy drive system today. It consists of a couple of cards. There's this one, which is the channel board, and this one, which is the interface card. The channel board deals with all input and output with the processor itself, and the interface card deals with in-out operations with the actual floppy drive itself. Channel card is quite interesting. It uses Intel's 3000 series bit slice processors, which are these things here. There's actually 4 of them on there because they're actually only 2-bit wide, and they're not a full processor either. They're a sort of 2-bit ALU shift register type affair. They can't do memory fetches or anything, so they have to be accompanied by this one here, which is a 3001, which is a micro program controller. I think I've got that right. And in addition to that, we've got the firmware, which is stored on these 4 ROMs here. So quite an involved setup, typical Intel. Obviously, the idea is to offload a lot of the processing load onto this card away from the processor. Have a quick look at each board in turn. Shift that in there. The only setting on this board is this little dip switch in the corner here, which has to be set to 78 hex for a double density system, and this being the boot drive. The switch probably looks a bit confusing if you can see it. Switches 1, 2 and 3 are actually just purely cosmetic anyway. This is the high byte and that's the low byte. It looks confusing because, as you may remember, the MDS has an inverted address bus. So effectively all these switches look back to front because when they're on, they represent a logic 0. So that's that one. Let me just get that one out of the way and I'll show you the other card. Right, this is the card that's connected directly to the floppy drive itself. Again, there's only one setting on this card as well, and that's this little what looks like a circular wheel, and that sets the interrupt, and that needs to be set to IRQ2. So that's that one. The 2 cards are joined via this connector here called the P2 connector, and you may remember from the first video I showed you these, which are P2 coupling connectors, but these were for a MDS Series 2 machine. Now I've had to remanufacture the board because the actual pitch is completely different in the MDS-800. If I hold them up side by side, you see that the MDS-800 has got a slightly wider board spacing. Another thing as well which I've discovered is that the height's different as well. If you were to use these connectors as they stand, the top here will actually be too high, and it would push the P1 connector, as it's called here, out of its socket. So if you look at the ears on the end of the sockets, hopefully you can see that the on the right, the green connector has got a much narrower ear, or whatever you want to call it, on the end there. I've had to reduce that down to about 4mm from its original size, which was the same as the black ones, and that effectively drops this one down into the chassis a bit. It makes everything line up. Right, this one's not actually finished yet because it's I haven't soldered it, but the finished one's in the NDS at the moment. So that's that bit. So that couples the 2 boards together. Obviously then we need some way of connecting this board to the floppy drive. The channel card only connects to the P2 and the P1 connector in the MDS. Right, so the first cable we've got is this one here. Right, now this connector plugs onto there. I'll show you this when it's in the system, because it's a bit confusing as it stands. just shift this out of the way. Right, so what we've got here, that goes onto the connector on the card, then that goes to two 37Y D connectors, and there's one for drive 0 and 1 and one for 2 and 3. Now where it goes from there is a little bit different on mine as it would be normally. Let me just show you what it should look like. If I bring a drive in, there we go. You have the back of the 8-inch drive. I'll just pull the camera up a little bit so you can see properly. Right, there you go. Gigantic 8-inch drive. Now normally on an Intel system there'd be a little board on the back here, a little printed circuit board, about 3 inches high, and that would go to a connector on the top, which would then go to the back panel of the disk enclosure to a 50-way connector, and then from that 50-way connector there would be a cable that went from the 37-way one we've just seen to that 50-way. Mine's been done a little bit differently to that. What mine's got is this ribbon cable. The ribbon cable goes straight on the back of the drive there, and it goes straight to a 37-way. It's interesting to say the least. Someone's been quite creative. I don't know if you can see all the little loops and things, but it's quite interesting on that side. You can see where they've sort of swapped all the wires over and that. I've checked it through and it's all correct, but you know, it is quite interesting. I think you can see some wires sort of skipping about here, and this one here it's got wires skipping over the top. So yeah, it's an interesting design. So it does all check out, so that's not a problem. You need to set some jumpers on the drive. They're listed in the manual though. They're basically all over the place. There's some terminators here, there's drive select, there's various other bits and pieces. If anyone needs to know any of these jumpers, they're all in the manual, or you know, drop me a comment, I'll let you know. This particular drive is not one of the ones that came with the system. This is an 801, which is out of my Altair system. Reason being is that I know this drive works. There's a little strap somewhere, can't remember, I think it's that one, and that turns it from an 801 into an 800. The only difference between an 801 and 800 is an 801 is a hard sectored drive, and the Intel uses soft sectored, so the little strap just turns it into an 800. The drives I got with the system have been stored somewhere damp, and although I have cleaned one up, it's got a couple of faults on it, so we'll look at those in a later video. Right, so we'll go over to the MDS and plug all this in. Right, we're back over at the MDS. Things to note at this point is that I've installed the channel card in slot 14 and the interface card in slot 15. The interface card needs to be in a higher priority slot, and the odd numbered slots have the highest priority. Also, the floppy cable is plugged into the interface card, and as well as that, this is an old style connector with the black top. That means the cables need to face towards the front of the MDS. If you've got the newer blue style, you know, similar to these ones, then the cables need to go to the rear of the MDS. That's just a point of reference there. Right, let me just get the camera around a bit so we can see all the bits and pieces. Right, down. I think everything's in shot now. Right, so what should happen? We'll follow the sort of normal boot up sequence. I've already got a floppy in the drive, by the way. It's just a scratch disk, so the system won't actually boot. But what we're at this point, we're just trying to find out, you know, if the system's going to try and detect the floppy drive and spin it up, basically. What I'll do, switch the MDS on. We'll depress the boot switch, hit reset. At that point, it should select the floppy drive, and we'll see the light come on the front, and it will probably initialize IRQ2 as well. At that point I'll hit space on the keyboard, release the boot switch, and that should start the boot process. Obviously there won't be a boot process at this point because it's not a proper boot disk. Right, let me just plug the drive in. Right, so the drive's spun up now, and these sort of drives actually run continuously. That's what you can hear it spinning. Right, I'll just go up a bit on the monitor. I think you can just about see the drive. Try and get both in at the same time. Okay, right, so let's start up the MDS. Power it up, put the boot switch, hit reset. Right, so we notice immediately the light's not coming on the floppy, and that's not a good sign, and we haven't got an IRQ2. If I press space on the keyboard, you can probably see, I'll just go up a little bit, the monitor looks like it's going to sign on until we release the boot switch. Yeah, it's gone straight into the monitor, so it's clearly not even seen that the floppy's there. You may remember that when we were stepping through the boot ROM with the logic analyzer, I mentioned that the system checked port 78 hex to see if the floppy drive was ready. So obviously this is a good place to check for it, to start our diagnostic process. So we'll write a very crude little program. So I'll do substitute 2000, dB for input, port 78, and I'll stick a no op in there. There we go. We'll run that program. Go 2000, breakpoint it at 2002. Right, there we go. Now, what happens when you do an input instruction is that the contents of the port will end up in the accumulator. So if I display the registers, right, here we go. Now this is obviously an indication of our problem, is that we've got 00 here. What the monitor ROM looks for is a 1 in the bottom byte, which signifies the drive's ready. And it rotates that into the carry, and if there's a carry set, then it jumps off into the disk boot loader. Now that looks like just an empty port. I can demonstrate that by changing the figures. If I put S2000 that one, isn't it, A0, so we'll check port A0 this time. I'll run it again. Yeah, so registers, and again we're getting 00. Now, try a port that's actually got something on it. Let's do S2000, F5 should have something on it. Go 2000, 2. Right, then you see we've actually got a value there. So it looks like a pretty fundamental problem that it's highly likely that the channel board isn't even being selected. So what I'll do, I'll set it up in the extender card and let it probe around, see if we can see what's going on. Okay. Right, all set up then. I think from the results we've had so far, what we're looking for is something sort of fairly basic, as in the board isn't even being selected. If we look at the diagram here, these are the switches I mentioned earlier on the board, and this set of gates here are effectively doing the decoding of the upper address lines. The first port call, I'm going to try probing here on pin 4 of A18, see what we get. See if we're going to get any pulsing at all. Right, let's try that first. Let's swap over the screen. Okay, so let's just find A18, pin 4. Right, okay, that's didn't work very well, did it? Right, that's low at the moment. Right, if we do an in 78, right, there's a flash there. Right, again. Right, so we're definitely getting selection there. So it's okay at that point. Let's go back to the diagram. Right, if we move over a little bit, we're now looking at these devices here. This one here is decoding the lower address bits. If we sort of scroll back over here, you can see we've got A01. That's interesting. There seems to be two ones there. That looks a bit peculiar. Anyway, oh no, it's just a extra connection. So the next port of call, we've come out of pin 4 here. We're going to go through this gate here, and we're going to go into here. So what we'll do, for a start, let's probe pins 5 and 4, which are the enables on this 3 to 8 line decoder chip, and that is A20. Right, okay, so swap back to there. 20's here. Well, that's high as we'd expect. In 78. Right, okay, we're getting a flash there. Let's try it again. Right, definitely getting a flash there. Right, so we're okay at that point. So up to here, we're okay. Pin 6 needs to be high. Yeah, it's pin 6. This drawing's absolutely shocking. Right, let's just check pin 6. Okay, yeah. Right, so pin 6 is definitely high, and that's good. Right, now what we want to do now, we need to be looking at the outputs of this gate here. Now, in theory, 78 is the base address, so that'll be pulling this line low, which is pin 15 on A20. Right, so let's just go back to terminal again. We'll go to A20. There we go. Right, we're on there. We'll do in. Oh, got it wrong. In 78. Right, absolutely nothing. And worryingly as well, as you might have noticed, look, it's not really high. See, that's the power supply row. See, that's quite bright. If I go down a pin, there's nothing there at all. It's just floating, and they're all like it as well. Look, all the outputs. And there's one on the other side as well, if I can get to it. Let's try that one. Right, that looks like an open circuit chip. So I'm going to have to change that one. This looks a bit like the problem we had with 3404 on the RAM card. Right, so let me get that swapped out and then we'll give it another try. Right, I've replaced the 3205 3 to 8 line decoder. I've actually put a 74LS138 in it, but it's the similar device. We'll get a proper 3205 at some point. What we'll do now is let's see if we can get some status back from the channel board. So if we do in 78, right, and now we're actually getting a value now. Notice we're getting 18 hex. If we look at my little awful diagram here, what that means is we've got D4 up and D3. D4 means it's a double density controller, which it is, and D3 being a 1 means the controller's present. Now what we're interested in now is the ready line on the bottom here, which currently is a 0. So if I start the drive up, in a sec. Right, drive's running. What I'll do now is I'll insert a disc, shut the door, and if we do another in 78, right, we're now getting 1D. We've got back at our little diagram, so the ready lines come up, that's the, and we've got an interrupt as well. That's what the D2 is. So in fact, I think probably, let me just swing the camera around a little bit. You can probably see that the interrupt 2 lights actually come on down there. So that's a reasonable sign. That means the interface card's actually generating interrupts. Right, what we should do now is try and boot the system, because we know we've got communication between the two cards and we're getting status. I've got a proper boot disk in this time. So what we'll do, I'll pan the camera down a little bit further. Right, keep an eye on the head load button here when I do the reset. So what I'll do, I'll press boot and I'll hit reset. Right, hopefully you saw that, but you see the load buttons move back to track 0, and if I shift the drive back, hopefully I might need to tilt the drive up, but you see the drive access lights on now as well, so that's a pretty good sign. What isn't a good sign is that the interrupt to light isn't on. We'll try and continue the boot process and see what happens. So I'll press space on the keyboard and I'll release the boot switch. Right, nothing's happening, so we've obviously still got a problem. What we can be confident at this point is though that the system the processor on the channel card must be running, and it must be communicating with the interface card, because obviously the interface card is driving the floppy and the channel board is giving us the status back, and there's no direct connection between the channel and the drive, of course, other than via the interface. So all of that sort of stuff must be working. The problem now may be is that we're not getting data back from the drive. There's definitely data coming out of this drive because I've tested it, but presumably it's not getting through the interface card to the channel card for whatever reason. So that's what we'll look at next. Right, I'm going to try and figure out what's happening with the read data. Luckily the manual gives you this quite detailed timing diagram. You see the read data on the 3rd line down. It's all dependent on this 2F clock, which they're suggesting you test on IC A18 pin 11. I've checked that, there's nothing there. So I followed things back. So just swap over. The 2F clock originates from this IC here, which is dividing down the system clock generator, which is 8 megahertz, which is over here. You follow that line up around here, it goes into the clock input here. It's basically a serial shift register. So what we'll do, we'll have a little probe along these pins, and I'll just show you what's happening, then we'll look at this IC in a bit more detail. Right, I'll pan down to the scope. Unfortunately the scope's got a really shiny screen on it, so I apologise for that, but hopefully you can see what's happening. Right, so what we'll do, we'll look at pin 8 first, which is the clock. So I'll go across to here. Right, that's the clock, that's the 8 megahertz clock. Now pin 9 is the head load. Now that should be high. That's pin 9, which it is, that's high. Now if we carry on going up, pin 10 is QD, that's high. The next pin is QE, and now bizarrely QE pin 11 is actually running at 8 megahertz, which is really strange. The next pin up is QF, that's low, and QG, which is the last one, is low again. If I go to the other side of the chip, we see that pin 1 is high, which we'd expect. Pin 2 is high. Pin 3 is high. 4 is high. 5 is high. And 6 is high as well. Right, so that's what we've got. Let's go back to the diagram. What I'll do, I'll just shut everything off because it's obviously getting a bit noisy. Right, so just to sort of, let me get a bit further up so we can see what we're doing. Okay, so basically this, what should be happening is that this 8 megahertz clock should be being divided down. And what we've seen, if we just, from the scope, we've seen that the bottom ones here, QA up to QE, is it QE? QE, yeah, sorry, I think I missed one out, didn't I? They're all high. Q11, QF, sorry, has got 8 megahertz coming out of it, and QG is low, and QH is low as well. So it's really, really odd. So if we look at the inside of the chip, swap over to here. Now, as we saw earlier, both pins 2 and 1 were high. So this is a NAND gate, so it'll be low at that point. It'll then be inverted into a 1, which will set this RS flip-flop here. And then that should gradually progress its way through all these flip-flops on each clock pulse, which is coming in here. That's where the 8 megahertz clock was. The clear line, which is from the head load, we saw was high, so that won't be affecting matters. But the question is, why is it that out of QF, this one here, we're getting 8 megahertz? Now that can't really be possible. This seems to be another problem inside the chip. So it looks like we're going to have to change that one, because I can't explain why it could possibly do that, because our clock effectively has got to work its way through all these RS flip-flops, and there's no way that if it had worked its way all through the flip-flops it'd still be 8 megahertz. So that seems to be the crux of the problem. So I'm going to change that out now, and then we'll have another go. Right, I've replaced the 74164. We're all set up ready for another go. We're just sitting at the monitor prompt at the moment. I've got a disk loaded, so we'll go through the boot process and hope we have more success than last time. Right, so the first thing to do is to depress the boot switch and hit reset. If I get my hand around that way, you should be able to see the head go backwards, which it has. And you'll also notice that the interrupt 2 light has come on. Now when I press the space bar, that should go out, which it does. And the next part of the boot process is to release the boot switch. Head's reloaded. Let's move forward a couple of tracks, and there we go. There's the ISIS 2 prompt. I'll move the camera up a little bit now so you can see what's going on. Let's see if we can get a directory on there. There we go. I'll try running something. Let's try PLM 80. Obviously this will run an error because I haven't got a source file, but at least it'll prove it'll load. Okay, let's try copying a file, see if we can actually write something. So if we do copy PLM 80 to PLZ 80, say. Okay, move the camera down so you can see the head moving. Okay, it's copied the file. Do another directory. And there we have our PLZ80. Let's try that. Z80. There you go. So all looks good. So that'll do it for this video, and I shall see you next time.